Okay, so this is the Prelab video for the electronic structure of atoms. This experiment introduces students to some of the observations that support the idea of quantization in matter and energy. All right, so it may be your first foray into quantum mechanics. Don't worry though, the math is still pretty simple. I'm going to talk about light for a second, visible light, and you see there in the image the color of the rainbow. And that is electromagnetic radiation, and that is the narrow region right here, which it exists, all right, in wavelength, right? In wavelength. Here is wavelength in meters. So visible light stretches over that narrow range of wavelengths, and that's what we can see. But there are other kinds of electromagnetic radiation. We have radio, and then microwave, infrared, ultraviolet, X-ray, and gamma ray bursts, on up here at very high energies. This is very low energy. Okay, but this region down here, that's the light that we can see. All right. Now, you've probably seen this before. White light, what we see as white light, can be split into its component colors using a prism, and that's what's done here. So the light we can see is in different wavelengths, and the prism separates this light according to wavelengths. Now, I want to introduce the aspect of light being a particle. And everything is quantized in this universe, apparently. I don't know, maybe gravity isn't, but that's another topic. Everything is quantized, and light is similarly, all right, arranged. It is quantized, and so light is really particles. These particles have both wavelength and frequency characteristics, all right, associated, well, with it being a wave. The wave is in the form of an oscillation of electric and magnetic fields. But it's really a particle that just has wave characteristics. That's the best way to look at light. All right? So, these particles that strike our eye and allow us to see color can be thought of as being red particles, red-colored particles, and blue-colored particles. Right? Yellow particles, green particles, so forth and so on. I want to talk about the energy of these particles. These particles have energy, and right up here you can see a plot or a direction where we have low energy over here and high energy over here. So the blue particles will have higher energy. We call these particles photons, by the way, so I'm going to continue to refer to them as photons. So blue photons have a higher energy than red photons. Red photons. Okay, let's talk about some of the mathematical descriptions of these particles. And don't get too upset, don't get freaked out. The math is pretty simple. First off, first equation, and you'll need to be aware of these equations. It'll probably show up on a quiz or an exam. C equals lambda times nu. Right? This little V looking thing here is the Greek letter we call nu. Okay? C is a constant, it's a universal constant. It is the speed of light. And C has a value of 3.00 times 10 to the 8 meters per second. Okay? So the speed of light is very, very fast. I think it can circle the Earth in about 7 times in a second. Right? So it's fast. It's fast. Lambda is a sign for wavelength. Okay? And usually when we talk about in this experiment and mostly in class, wavelength is in units of nanometers. All right? So a billionth of a meter. Frequency is in units of inverse second. All right? Inverse second, typically. Now, C being a constant, that means wavelength, I'm going to have to stop doing that. Maybe I can change that to autofocus lock. wavelength and frequency are proportional. This has to remain constant. In other words, when wavelength increases, frequency has to decrease. And the reverse is true. Okay? So whatever this value over here is, like lambda, whatever the wavelength is, that sets the value for frequency because it has to keep C constant. That's the best way to look at this. So from this, we get both the wavelength of the photon and the frequency of the photon. What about the energy of the photon? Energy of the photon is described by this equation. E equals Planck's constant times nu, frequency. This is the energy of the photon. One photon has this energy. So if you know the frequency of that photon, you can determine the energy of that photon. This is Planck's constant, and Planck's constant has a value, see if I can remember, 6.626 times 10 to the minus 34, and units are frequently shown as joule seconds. Joule seconds. Right. Not joule per second, but joule seconds. Right. So this shows up on an exam or a quiz. You need to know these two equations, but I will give you the value of these constants. Right? You don't have to remember the value of the constants. I'll give those to you on a quiz. Okay. So, the take-home point here is that light is a particle that has wave characteristics, and the wave characteristics are kind of described by these two equations. One other thing I want to show you here, we can combine these two equations, all right, to get a new equation. So the energy of the photon can also be described as h over c times wavelength. Okay? So basically I just solved for frequency using this equation. Right? So I divide both sides by the wavelength. I get c over lambda equals frequency. And plug that in over here. Okay? So this also describes the energy of a photon, this equation. Okay. Next thing. An energy level diagram can be written, and we're going to write one for hydrogen atom. And I'm assuming you've read some of the background material already that I posted on Canvas. All right, the department handout and the write-up that I provided. Energy level diagram describes the energy states available to an electron inside a hydrogen atom. In a hydrogen atom, the energy states available are pretty simply arranged. That's why we use hydrogen as our introduction. That's also why hydrogen was used as the first model that incorporated quantum mechanics. Anyway, that's a historical fact I'm not going to go into. N right here is the principal quantum number, all right, for this energy state. And if an electron occupies this energy state, it also has its principal quantum number, 1. This principal quantum number 2, 3, 4, 5, 6, and so on. And they go on up, right? They go on up. Now these are energy states available to the electron inside a hydrogen atom. And only these energy states are available to the electron. In other words, an electron can't just have any old energy when it's inside a hydrogen. Right? It's quantized. Only certain quantized states are available to an electron. Now let's suppose that an electron is up here. It's in the energy state available to it, and it's described by the principal quantum number of 4. Now this would be an excited state hydrogen atom. And ground state hydrogen atom is when all the electrons are in the lowest states available to them. So a ground state hydrogen would be an electron residing in the first quantum, the first level. But this is an excited state. So this electron's up in excited state. It's excited. it has a higher energy than if it were down here at a lower energy level. Now these electrons will relax. They don't always remain in these higher energy levels. It can fall back down. Right? It can fall back down to 3, it can fall back down to 2. So let's imagine that this electron relaxes down to the second energy level. Now, I don't want you to think that this electron passes through these energy levels. It doesn't. All right, it doesn't. It just transitions. Right? It's instantaneous. When it goes through this process, it never stops at 3. It never has an energy state of 3. It transitions from 4 to 2. Now, the energy of this electron is higher when it's up here, and it's lower when it's down here at 2. So this process, the electron loses energy. Now that energy has to go somewhere. Energy can't just disappear in the universe. The energy in the universe is constant, as far as we know. So this energy change of the electron is manifested in the release of a photon, one of these light particles we're talking about. And I'll represent that by this wavy little thing coming out. So this relaxation process produces a photon. That photon is emitted, and that photon can actually come screaming out and hit us in the eye. And if the frequency of the photon is the right value, we can see it. We see it as color. We see that photon as color. Now let's talk about this. Energy difference here. Energy difference between 4 and 2. So the energy change from 4 to 2. That's how I'm going to represent it. And this equals just delta E. All right. This is the energy change of the electron. Energy change of the electron. The energy change of the electron must equal the energy of the photon. Right? The loss of energy equals the energy of the photon that was released. So delta E also equals Planck's constant times its frequency. Okay. Next thing. Let's consider 2 cases here. Another energy level diagram. And I'm just going to start with 2. This is 3. And we have an energy level diagram over here. We're going to look at 2 cases. Two, 3, 4. Okay. So we'll look at the same transition that we had up here, 4 to 2. So this electron is relaxing down to 2. Let's say we have an electron here at 3, and it also relaxed to 2. Okay. So these are 2 different atoms, and they have 2 different relaxation processes. A photon is emitted here, and a photon is also emitted here. Now, these photons are going to have different energies. They have different energies. This one will be a higher energy photon, right, because the energy change here is greater. It's going from 4 to 2. This one will be a lower energy photon because the energy change is smaller. It's just going from 3 to 2. Lower energy photon, higher energy photon. Okay. Just think about that just for a second. Let me switch back over here. Drop the lock. So perhaps in the 3 to 2 transition, it's going to be lower energy. Perhaps that photon shows up over here. It's in this region somewhere. Right? It's lower energy, right? This is the lower energy segment. So maybe that photon that's released from the 3 to 2 transition shows up over here. Maybe the photon released from the 4 to 2 transition, remember it has a higher energy. Maybe it shows up over, I don't know if this happens to your monitor, but my monitor. Okay. The 4 to 2 transition, maybe that happens right here. So it's possible out of this continuous spectrum, right, if we're just looking at the transitions, we will get a color band there for the 3 to 2, and a color band right here for the 4 to 2. Look at this. These are emission tubes, and you can read the caption down below here. These emission tubes have a gas in them. Right? Mercury is on the far left. Mercury can be a gas. I mean, it's a liquid metal, but you can excite it. You can heat it when it's ionized with electricity. It goes into the gas phase. The middle one is helium, and the one that's on the far right is hydrogen. So let's look at the hydrogen. It's right here. The gas is contained in this tube, and electricity is passed through it, and that excites the gas, and it excites the electrons that are within the gas. Those electrons are excited, but they relax back down to our lower energy state. And remember, the relaxation process causes photons to be emitted, and those photons come screaming out and hit our eye, and that's what we see as the color associated with hydrogen. So we can take this tube, we can take this hydrogen tube, emission tube, and we can run it through a prism, just like we're doing here. Right. We're going to do this in this experiment. Well, we won't do it for hydrogen, we'll do it from other noble gases. Run it through a prism, and we can separate the component lights, the component light of hydrogen, into its different bands. And so we can separate the individual transitions. And those individual transitions show up in these colored regions over here. Okay. So it's not a continuous spectrum that you see with white light. Only the few transitions available in hydrogen are we going to see when we do this experiment. So switch this out. This is in color because I don't have a color printer. I want you to think for a second. So which side is going to be red or blue according to wavelength here? All right, this is the hydrogen emission lines, right, the individual transitions. If we took a hydrogen emission tube and we separate it into component colors, this is the emission spectrum that we would get for it. This is a higher wavelength. This is a lower wavelength. So red must be over here, and violet must be over here. Now, according to C equals lambda nu, larger wavelength means a lower frequency. Right, when this goes up, this has to go down to keep C constant. Longer wavelength, lower frequency. Over here, we have a shorter wavelength. Shorter wavelength, higher frequency. So according to this equation then, these have a higher frequency, they must have higher energy. This transition must have a higher energy because this is a higher frequency. Shorter wavelength, higher frequency. Longer wavelength, shorter frequency. So these are lower energy photons from this emission line. Okay, so the Balmer series, that's what this is called, the Balmer series emission. All the electrons end up in the principal quantum number of 2. All right, that's where they relax 2. Okay, they all stop at 2. It doesn't mean all the electrons are going to stop at 2. There are other transitions that go to 1, but transitions that end at 1 are in the ultraviolet range. All right, it's a region of the electromagnetic spectrum that we can't see. So each one of these transitions will have a final stop. The electrons that relax will have a final stop at the principal quantum number of 2, or the second shell. So this is a higher energy transition right here, the higher energy transition. This transition, the photons that we see for this band, are produced when an electron transitions from 6 to 2. Over here is the next highest energy. That's produced when electrons transition from 5 to 2. So the photons that are emitted here show up at 410. The photons that are emitted here show up at 434. Next highest energy, 486. That is the 4 to 2 transition. And way over here, we have 3 to 2 transition. And these are the only transitions that produce photons in the visible region of the electromagnetic spectrum. Now that's the electronic structure of hydrogen. Now I want to say again, there are other transitions available, and they occur. For example, there is a 2 to 1. There's a 2 to 1. And the 2 to 1 will produce a higher energy photon that will be in the ultraviolet. There are also 6 to 5 or 6 to 4. And those are lower energy transitions, and they produce photons that we see in the infrared. Okay, so we can't, well, see them. We can't see them, but those are photons that are infrared region. And anything that goes down to 1 will be photons that have wavelengths in the ultraviolet region, so very high energies. Now, it may not be exactly clear here because these spacings that I've drawn here are not to scale. It turns out that the real spacing, energy spacing, would be something like this. 1 would be down here. 2 would be up here. 3 would be a little bit closer to it. 4 would be closer still. And 5 would be even closer. Right? That's the real energy level spacings, or a more realistic representation of the energy level spacings in hydrogen. Okay? They're not evenly spaced like I've shown over here. Okay? All right, next idea. These are the energy spacings for hydrogen. Other atoms will have different energy spacings. So maybe we had one atom that has energy spacings that look like this. Okay? There could be another atom, different element, that has energy spacings that look maybe like so. It could be more complex. They're not all simple like hydrogen. So you have different transitions available over here that produce different wavelengths of photons, and different transitions over here compared to this one that also produce different wavelengths of photons. And so these emission spectra that we see can be like a fingerprint. Hydrogen will produce a visible spectrum of just 4 lines. 4 lines. That's what hydrogen will produce. Other elements will produce more complex emission spectra. Here's an example here. So this is helium. So helium has 1, 2, 3, 4, 5. Barium. Barium produces a quite different set of emission bands. And so these are like fingerprints. We can use this to analyze to determine elements that are present in a particular sample. It just doesn't hold to atoms. Molecules can also behave this way. So this is some of the quantized phenomena. What you're seeing are quantized effects inside atoms, the quantized aspects of electrons transitioning to only certain allowed energy states. And that's where we get the term quantization. Quantization. So, all right. One last thing. And you're going to have to do this. It's not used a whole lot anymore, honestly, but it is part of the work assignment. I want to talk about the Rydberg equation. The Rydberg equation. 1 over lambda equals R, this is the Rydberg constant, 1 over N final squared minus 1 over N initial squared. All right, so we'll do the energy spacing again for hydrogen. So this is 2, 3, 4, 5. Those are the principal quantum numbers, or the shells in hydrogen. Energy is increasing this way, going up. All right, so how do you use this Rydberg equation? Let's look at the 4 to 2 transition. 4 to 2 transition. So 4 to 2. The initial principal quantum number of the electron is 4. Right? So Ni, in initial, would be 4 here. The final principal quantum number is 2. The electron transitions to 2. So N final would be 2. So in this case, this equation would become this. 1 over lambda equals the Rydberg constant times 1 over N final, is 2, 2 squared, minus 1 over the initial, 4 squared. Okay. And depending on the constant over here, right, you'll get a value for 1 over wavelength. Right. It's important to remember, and I've seen this time and again, maybe about half of you will do this calculation and give the value for this calculation as the wavelength. Doing this over here does not give you wavelength, it gives you 1 over wavelength. 1 over wavelength. And so you need to take the inverse of that to get actual wavelength. Okay? All right. Now this Rydberg constant will be given to you. And in the department handout, it gives you the value in inverse centimeters. But if you see it on an exam, I will actually give this value to you, and it will be in inverse nanometers. Inverse nanometers. But depending on this value here, determines, depending on the units over here, determines the units over here. There are no units in the brackets over here, right? No significant figures. These are counting numbers. They're quantum numbers, right? Counting numbers. All right, so that's it for the Rydberg equation. Last thing, a bit about this experiment. So we're going to analyze some light sources. We're going to send them through a prism of sorts, and we're going to look at the emission spectra of these light sources. Right? Don't have a prism. We have something called a fraction grating, right? This little piece of plastic, and it acts just like a prism. I'm not sure that it's going to show up here. Yeah, you can kind of see that it's diffracting, right? Get different lines, but if you look at a light source through this piece of plastic, yeah, you can start to see some of the rainbow there. It will split the lights into component colors. Okay? So we'll use this to look at some of our light sources, and you should be able to see different colors, all right, split into different colors from those light sources. I'll explain more when I actually do the experiment. So this is the prism of sorts that we're going to be using. We're also going to use this. Right? This is a spectroscope, what we call a spectroscope. The light source actually comes through this little slit here. There's a diffraction grating on this side, and you look through this hole. And there's also a little ruler in here that measures wavelength, but we can't use that. It won't show up on the camera that I have here. But look through here, and you can see the component colors that are within a particular light source. And so we're going to use this in our experiment as well. All right, that's all the background information I have for the experiment. Talk to you guys later.